Hello everyone, welcome to my talk. My name is Chandranil and today I'm going to talk about learning IO-access patterns to improve prefetching in solid-state drives. The paper was co-authored by my research advisor, Heiner Litz. Prefetching is the process of preloading data from a slower storage device to a faster memory. It can be implemented either in the operating system or within the storage system controller itself. To summarize our contributions for this project, we address three challenges of prefetching in SSDs, namely timeliness, coverage, and accuracy. We propose a neural network-based prefetching technique that outperforms the state-of-the-art by 8 times on real-world traces. We also propose an address mapping learning technique that demonstrates the practicality of our approach in unseen SSD workloads. Now, there are three important metrics to compare prefetchers, namely accuracy, coverage, and timeliness. Coverage is the ratio of the SSD reads that are prefetched versus the total number of SSD reads. Accuracy is the number of prefetched data blocks that were actually utilized by later demand reads. And timeliness deems that the blocks to be present in DRAM whenever requested. An ideal prefetcher must generate accurate prefetches in a timely manner and has coverage throughout the entire SSD. Here we introduce our neural network-based prefetching architecture. The trace data containing information about timestamp, IO size, and offset are used to train the neural network model. The trained model generates predictions ahead of time to compensate for the inference latency and also time to bring the blocks to DRAM. Every IO access is checked against the cache to see if the LBA is present, then it's recorded as hit, otherwise a miss. We choose variable cache sizes of LBA for the stride, and we use Markov chain-based predictor, a stride prefetcher, and knife prefetcher to compare our work. In this slide, we introduce our neural network-based model architecture. We design our proposed model to predict both IO size and LBA at the same time. The model has two separate input layers, one for IO size and one for LBA deltas, where each input layer is an embedding layer consisting of 500 neurons. The model has two hidden LSTM layers, where each one has 500 hidden neurons. The outputs of the two embedding layers were first concatenated and then fed to the shared LSTM layers. The final output layer is split into two branches, where each branch is a dense layer consisting of softmax nodes. For our experiments, we used a total of 10 block-level IO traces from 3 different sources running live applications in servers. The data sets include traces from Microsoft Storage Network Association, SNIA, Microsoft Research Cambridge, and Virtual Desktop Interface traces. Here we compared the performance of our approach with the baselines that we compared. From this table, you can see that our prefetcher consistently outperforms the baselines for each dataset we used. It delivered up to 11 times improvement on stride prefetching for Microsoft SNIA traces. It also achieved the highest precision and recall among the baselines. The Markov chain predictor, on the other hand, performed worse than even the knife prefetcher in several cases. For VDI traces, we achieved the highest accuracy, providing up to 800 times improvement over the stride prefetcher. So to conclude, we showed how to leverage neural network models to predict future IO accesses and achieve generalization across workloads by leveraging a large set of real-world workloads. We compared the performance of our prefetcher with state-of-the-art techniques and used an in-house simulator to test the accuracy, coverage, and timeliness of our prefetches. We showed that our proposed model outperformed prior approaches by 8 times and by stride prefetcher by up to 800 times on real-world workloads. That concludes my talk. Thank you for listening.